All right, so we've talked about the dot product, which we also call a scalar product because the dot product just gives you a number as a scalar. And we saw that the dot product formula involved the cosine of the angle between two vectors. So it kind of makes sense to have another product formula that involves the sine of the angle between the vectors. And this is called the cross product. It's also, the cross is also referred to as a vector product because unlike the dot product, it will actually produce another vector. So here's our definition. If we have two vectors u and v, the cross product will be the magnitude of u times the magnitude of v times the sine of the angle between them. That alone is going to give you a scalar, this part right here. So then we multiply that by a vector n we'll call, where n is a unit vector that is perpendicular to both u and v, as determined by the right-hand rule. So we'll try to explain this here. So for example, if I take the unit vectors I and j, we know I and j are perpendicular vectors, right? I is pointing in the x direction, j is pointing in the y direction. If I were to do the cross product, it would be the magnitude of I times the magnitude of j. Both of those are 1. The angle between them is 90, it's 1. And then I would have to find a vector that's perpendicular to both of them according to the right-hand rule. What the right-hand rule says is, imagine taking your right hand, so there's my picture, and around I, because we're crossing I into j, so you put your right hand along the vector from the arrow, from the end to the head of it, where the arrow is. And then imagine pulling this vector into j, like forcing it into j. So for example, let's see if I can do this. If my two pens, if there's I and j, the pink pen is I, the green pen is j, I have my right hand on I, I'm gonna pull it into j like this. And notice my thumb is pointing upward in the direction of positive k. So that would be my unit vector that's perpendicular to both of them according to the right-hand rule. So I crossed with j would be k. I crossed with j would be k. You can do the same, and it's good practice here to try the following, to try to visualize the cross products, all the possible cross products of your unit vectors, I, j, and k. If you try to do j crossed with I, try putting your right hand on j, pull it into vector I, and you should see your thumb is pointing downward this time. It's pointing the opposite way. So this was just the opposite of the one we just modeled. So j crossed with I is negative k. If you try j crossed with k, you will get I. And one thing you'll notice, if you do it the other way, so j crossed with k is I, k crossed with j is negative I. That's typical. You'll get the opposite vector because you're doing it the opposite way. You're putting your right hand on the other vector first. K crossed with I, you should get j, which means I crossed with k would be negative j. Now, if you do a cross product of two of the same vectors, or any vector that's pointing in the same direction, I and I are pointing in the same direction, you're going to get 0 because the cross product involves the sine of the angle between them, which would be 0. Okay. So let's see how this works. So I have u equals I plus 3j, v is 5i plus 2j, and I want to find out what u cross v is. Now, u and v are both two-dimensional vectors. So I tried to plot these in the three-dimensional space. There's x, y. U would be pointing this way. You go over 1, up 3 in the y direction, and v would be pointing this way. So if you crossed u with v, if you can imagine putting your right hand on u and pulling it towards v, if you used your right hand, your thumb would have to be pointing down. So I can tell from the picture that the direction of the cross product should be pointing purely down in the negative z or the negative k direction. Now we can confirm that. And I want to show you that one way to do a cross product, it is a product, it is multiplication, And we did something similar with the dot product. You know, what would you do if you had x plus 3y times 5x plus 2y? You would FOIL it out. You would multiply it out. And it does work that way. So what you would do is you could take the coefficient, 1 times 5 gives me 5, but then I would have to do the cross product of I and I. But we know that came out to be 0. Then you would have 1i plus 2j. 1 times 2 is 2. And you would have to cross I and j. We figured out that that was k up above. You would have 3 times 5 is 15. And then you would do j crossed with I, which is negative k. And then finally 6, 3 times 2, 6, j crossed with j, but because they're in the same direction, that's going to be 0. So I only end up with 2k minus 15k. The cross product is negative 13k, which is pointing straight down as we suspected. You can do this with, so that one we could predict the direction. You can do this technique. I'll show you one more here. With three-dimensional vectors, here's a vector in 3 dimensions for u, a vector in 3 dimensions for v. Those would be very hard to visualize what direction, according to the right-hand rule, what direction my cross product vector should be pointing in. The math will tell us. So you can do the same thing. I don't want to walk through the whole thing, but you could multiply it out. And each time you multiply, you have to figure out what, I cross I, or I cross j, or I cross k. And we can do those values. We have them on the previous page. If you combine everything together, you end up with the vector negative 10i minus 7j minus k would be the cross product vector. And this vector is perpendicular to both of those, according to the right-hand rule. Okay, it works itself out when you do the math. Now that would be a lot of work. Every time we want to do a cross product of 2 3-dimensional vectors, having to expand it out that way. So is there an easier way? Of course. Well, not of course, but there happens to be, okay? So the common way to find a cross product is called the determinant method. And so a determinant is more of a linear algebra topic. Some of you might have some experience with determinants. If you don't, one of the courses you'll take after this and a few courses away is called 22A. It's a linear algebra course, and you will learn more about how determinants work, what they mean, what the properties are. Right now, this is just going to look like a magical process that's going to give us the correct answer for the cross product. So it's not a clear explanation for why this works, but all of that will get sorted out in 22A. Our job right now is not to try to interpret what a determinant is. Okay, we're just going to borrow it right now. Okay, so here's for that the same 2 vectors we just found the cross product for up here. If I want to find the cross product, I'm going to line up, okay, a determinant, you just put 2 straight lines, I, j, k. My first vector was 2i negative 3j plus 1k, and my second vector was 1i minus 2j plus 4k. Now, one thing I need to mention here, the determinant of, we call this a 2x2 matrix. You have 2 rows and 2 columns, is the product, you multiply the main, this is called the main diagonal. You do a times d, and you subtract c times b, or b times c. So it's the diagonals, a times d minus b times c. And it'll give you a number, and that's the determinant of a 2x2. Some of you may have seen that. That's typical in an algebra course. They might show you something about a 2x2 determinant. Now, the way we do a 3x3 determinant, we call this expanding along the top row. So what I mean by that is the top row is I, j, k, and we're going to start with the I, and we're going to take I and we're going to multiply it by the determinant that you get by covering up the row and the column that I is in. The row and the column that I is in is negative 3, 1, negative 2, 4. That's this determinant here. And we'll work out that determinant in a minute. So you do that times I. Then we move on to the j. And there's a reason for this. Again, it comes back to the property of determinants. that you need a negative there. You automatically get a negative on the j term. And then we do the same thing. We block out the row and the column that j is in. That leaves us with this determinant, 2, 1, 1, 4. And then we go back to plus for the k, and we block out the row and the column, and we have this determinant to work out. Okay, and then this determinant, when you do it, again, it's just this product, so negative 12 minus negative 2. That's really plus 2 then, so that would give us negative 10i, minus, and this will give us 8 minus 1 is 7, so minus 7j, negative 4 minus negative 3 is really negative 1, and I get negative 1k. And notice that's exactly the same answer we had previously, and much faster. And this process will be much faster as you practice it. You won't have to necessarily write out those determinants. You know, typically, like in the next one, when we do it, we'll just block out I, the row for I and j, and we'll just do that determinant in our head. And then we'll just go negative 12 minus negative 2, and we'll get that negative 10 really quickly. Okay. So we'll use this technique from now on for doing a cross product. Okay, so next question, and this will involve a cross product. We want to find a vector perpendicular to the plane x plus 2y plus 3z equals 6. We've talked a little bit about planes in 12.1. Most of the planes there were vertical or horizontal planes. So this plane, first of all, how I know it's a plane is I have x, y, and z, and they're all to the first power, equaling some number. Now a plane is defined by 3 points, just like a line is defined by 2 points. So to graph this plane, I just need to find 3 points, and 3 easy points to find are the intercepts. This plane, when it hits the z-axis, both your x and y values will be 0. So if I just put in 0 for x and y, 3z equals 6 gives me z equals 2. And I do the same thing for my y-intercept right here. If I let x and z be 0, y will be 3. And if I let y and z be 0, my x value is 6. If I connect those 3 points, you get what looks like a triangle, but that triangle is really a flat surface, isn't it? This triangle is a flat surface, which is a portion of the plane, x plus 2y plus 3z equals 6. The plane keeps going, okay? It goes in all directions. So what are we seeing with that triangle? We're seeing the portion of that plane in the first octant, right? If I kept going down this way, I'm going to go down to the negative z direction, right? And this is going to go into the negative x area. So we're only seeing the portion of the plane in the first octant. Now, one way to find a vector perpendicular we saw to 2 other vectors is to do a cross product. So I'm going to find a vector u here, which goes from b to c, and a vector v, which goes from b to a. And if I do the cross product, you can maybe be able to visualize this now, right? If I pull u into v, can't really do that, there we go. If I pull u into v, my thumb's going to be coming outward, away from the plane. And it will be perpendicular to both vectors. That will be a right angle, and this will be a right angle. Okay, so recall how to find a vector between 2 points. You can, to find vector u, it starts here and ends there, so you can go for each coordinate final minus initial, 0 minus 0, 0 minus 3, 2 minus 0. So I end up with 0, negative 3, 2. Doing the same thing for v gives me 6, negative 3, 0. And then we're going to do the cross product, because that will give us our vector n. So ijk, u is right here, v is here. Okay, we're going to do, so let's talk through how we got the 6 there. So for I, we're going to block out the row and the column that I is in. And then we're going to do the determinant. Negative 3 times 0 is 0, minus negative 6. 0 minus negative 6 gives you 6i. Remember, for j, there's automatically a minus. And then we'll go 0 times 0, 0 minus 6 times 2 minus 12. So 0 minus 12 is negative 12, but there was the negative out in front there, so that's actually positive 12. And then for k, 0 minus negative 18 gives us positive 18k. So a normal vector to this plane, a vector perpendicular to the plane, is 6i plus 12j plus 18k. Now there's something interesting about that answer. And this is a really important concept in 21C. We just found that the normal vector to the plane x plus 2y plus 3z equals 6 is this vector, which if I factor out a 6, gives me I plus 2j plus 3k. Notice, and so even just this vector right here is perpendicular to the plane, right? It's 6 units. It's 6 times smaller than this one, but it's still pointing in the same direction. And notice it has the same coefficients as the plane. So this is a very, very useful thing in 21C and totally counterintuitive. To me, anyhow, it's counterintuitive that if you want to find a vector perpendicular to this plane, 1x plus 2y plus 3z, perpendicular, that I can just choose a vector that has the same coefficients, and that vector is perpendicular to the plane. It's a little bit counterintuitive, but it is true. Okay, so we can use that fact. Let's say I want to find a vector perpendicular to 5x minus 17y plus 9z equals 1. I call this stealing the coefficients. I know for sure that if I just take 5i minus 17j plus 9k, that vector is guaranteed to be perpendicular to the plane. Okay, and then we can run it the other way. Let's say I want to find the equation of a plane that contains a certain point, and it's normal to, meaning perpendicular to, this vector right here. There's two methods we could do this. There's kind of the fast way to do it, and then maybe a more formal approach here. So I want to show you both methods. One method to take advantage of what we just learned is that if our plane is perpendicular to this vector, 3i minus 2j minus k, then we know the equation of the plane by stealing the coefficients would have to be 3x minus 2y minus 1z equals some number. I'm going to temporarily call it d. Now, how would I find that number? I could just plug in the point that they gave us. I could plug in 0 for x, 2 for y, and negative 1 for z. And if I work that all out, I get negative 3. So that would be my value for d. And there's the equation of the plane. Gotta move that up a little bit. There's the equation of the plane. Now, another way I could answer this question, and this is a more formal way, this is how the book does their problems in this section, is that I could take that vector that they gave us and place it directly over the point in the plane. Remember, a vector is just an arrow. You can move it wherever you want. And then I could make another vector from 0 to negative 1 to a random point x, y, z. This point right here is x, y, z. And how do I make that vector? Final minus initial, final minus initial, final minus initial. So my vector u is going to be x, y minus 2, z plus 1. Now, what do we know about these two vectors? They are perpendicular, right? One's in the plane, one is perpendicular to the plane. So if we go back to the dot product of those two vectors should be equal to 0. So if I do the dot product between that u and n, which is very easy, right? 3 times x plus negative 2 times y minus 2 plus negative 1 times z plus 1, that should give me 0. And if you distribute and clean it up and move, keep x, y, and z on one side, move the numbers over to the other side, you will find that you get the exact same answer that we got. Another feature about the cross product is it can actually be used to give you the area of a parallelogram. Recall, the area of a parallelogram is just the base this length times the vertical height of your parallelogram. If I take two vectors, u and v, that are not in the same direction, we say that u and v can span out a parallelogram. In other words, if you put u and v tail to tail, you could put another u here, another v, the vector there, another u vector there, and you get a nice parallelogram. So the area of that parallelogram would be the base, which would be the magnitude of v, times the height, and that's going to equal the magnitude of u times the sine of theta. I can show you why that's true. If I wanted to find the height there, I would go sine of theta is equal to the height over the magnitude of u. Right, opposite over hypotenuse. So if I was solving for the height, I would just multiply magnitude of u over times the sine of the angle. So this is the formula for the area of a parallelogram, and that also happens to be almost the full cross product. Of course, it's not a vector here, right? This is a scalar. So what that says is the area then would be the magnitude of the cross product, u cross v. And what if I wanted the area of a triangle? Like, for example, if I made a triangle ABC here, well, that would be clearly half of the area of the parallelogram. So if I want the area of a triangle, I can just do half the magnitude of a cross product. Strangely enough, this idea of using vectors to find the area of a parallelogram actually comes up again in 21D when we talk about finding surfaces, areas of surfaces in three-dimensional space. You can actually imagine any surface made up of a bunch of parallelograms, small parallelograms all connected to each other, and we take advantage of this formula to find the areas of all those parallelograms to give us the area of the surface. Okay. Now, if we bump up a parallelogram a notch in dimensions, you get something. If you have a box made up of parallelograms, every side is a parallelogram. It's actually called a parallelepiped. Okay, and that can be defined with 4 points, A, B, C, and D. Of course, I didn't try to graph this actually in three-dimensional space, but you can imagine A, B, C, and D being oriented in such a way that I could pick one point A to kind of be a corner here. And I could think of this parallelepiped as being spanned by three vectors, U, V, and W. U, V, and W. Right, because all this vector is W, that's W, right? And then there's U, there's V, there's V, there's V. They're all the same vectors there. Now the volume of a box of a parallelepiped is the area of the base times the height. And just like for a parallelogram, we're talking about the vertical height, straight up and down. Now we know the area of the base. The base is a parallelogram. And we just found out that the area of a parallelogram is the magnitude of u cross v. To find the vertical height, notice that from this vector w, if I drew a little auxiliary line here, right there, this length right here is the height. So if I thought of a little triangle there, there's an angle between what I'm looking for, the height here, and w, and so I would use the cosine function. I would say cosine of theta is h over the magnitude of w, and if you solve for h, you get the magnitude of w times the cosine of theta. That's the height. Now if you look at this formula, remember u cross v is a vector in and of itself. That's going to be a vector. So this is the magnitude of a vector times the magnitude of another vector times the cosine of the angle between them. By definition, that's a dot product. That's a dot product. Oh yeah, and by the way, u cross v, remember by the right-hand rule, that vector would actually be pointing upward in the same direction for the triangle we just used to find h, right? So u cross v, that angle theta is between u cross v and w. So this now becomes a dot product of the vector u cross v dotted with w. Now we take the absolute value because the dot product is a scalar, and it is possible you could get a negative answer, but of course volume is not negative. So here we mean absolute value, not magnitude. That's the absolute value to make sure we get a positive answer. Okay, so let's see how this works. Using the final minus initial, you should be able to get these for your vectors, u, v, and w. Maybe pause the video and make sure you agree with these vectors. So in our formula, we have to do u cross v. So we have I, j, and k. U is 1i minus 1j plus 2k, and v is 3i, 0k, 0j, and 6k. And if you do the cross product where you're blocking out and doing the determinants, blocking out the row and the columns, you should get negative 6i plus 3k. Then I would take this answer, u cross v, and dot it with w. So I would dot this. And remember the dot product, you're just multiplying and adding. So I get negative 12. There is no j here, so that was going to be 0. Minus 9, right? 3 times negative 3. So minus 12 minus 9 is negative 21. That's why we need to take the absolute value to make it positive. Okay. And so the volume of that parallelepiped is going to be 21. Now, one question I think that deserves attention is why in the world would we care about the volume of a parallelepiped, right? Who cares? For many of you, that's probably the first time you've ever seen that shape, right? So why would we care about that? One use of the parallelepiped formula for the volume of it is to answer a very, I think, reasonable question about three-dimensional space, okay? One common question that I think in an algebra class, in two-dimensional algebra, you should definitely know how to answer is that if I give you 3 points, we know between any 2 points there's a line, but if I give you 3 points, a good question to ask is, are all 3 of those points collinear, or do they all lie on the same line? If you think about the three-dimensional equivalent, any 3 points make up a plane. So I know I could make a plane that has these 3 points. But what I might want to know is if someone gives me a 4th point, does this point lie on the plane made up of those 3 points? In other words, are all 4 points coplanar? Okay. Now, so imagine trying to answer if 4 points in three-dimensional space are coplanar by graphing it. It's going to be really tough to visualize these 4 points in space if they really lie on the same plane, okay? But if you think about it, let me go back to my other picture. Okay, so we got a volume of our parallelepiped on the previous problem of 21, okay? So that has some legitimate volume. If, for example, in my picture, point D actually lied in the plane, right here, if point D was in the plane of A, B, and C, then there wouldn't have been any height to this box, right? I could still run the numbers, I could still talk about a vector W, but if point D had been right there in the plane, what would my volume have been? My volume would have been 0. So one way to check if 4 points are coplanar is if you compute the volume of the parallelepiped spanned by those 4 points and you get 0, then yes, all 4 of those points lie on the same plane. And it's a relatively simple way, certainly better than trying to graph these points, to answer the question if they are coplanar. So you can try this, work out your vectors, and then the way you could do it is just choose P randomly to kind of be like the base point. So you can use PQ for your U, PR for your V, and PS for your W vector. Use the formula for the volume of the parallelepiped, and in this case you actually do get 0, which tells us that all 4 of those points are indeed coplanar.